Hello, this video is part two about this little device that I made. It's an Arduino shield. So in part one, I discussed sort of what's on the board and what I intended to do with it. I wanted to use this light dependent resistor here to record some values of LEDs and different resistors. So if you haven't seen that video, this one might make more sense if you see that one first. But in this video here, I'd like to talk about basically what I did, just a quick summary of some of my results, and then more importantly, what it is I sort of learned from making this and playing around with it. Okay, so again, if you haven't seen the other video, I suggest watching it now. Otherwise, let me just briefly summarize what it is I did. So if you look at this picture here, this is basically what's on the shield. So there is a light dependent resistor here, and it's fed by 5 volts from the Arduino, and that's connected to a 10 kilo ohm resistor to ground. And then here in the middle, between this voltage divider, it goes to the Arduino analog pin A0. Right, so as the light resistor gets more light, it has a lower resistance. And so then this voltage, as seen by that analog pin, will be higher, and it'll get a higher reading. And then if there is, if it's darker, then that resistor, there's more resistance in that resistor, and then the voltage on that pin, that analog pin, would be less, right? So remember also with the Arduino, the values you can get on an analog pin is 0 to about 1023. Also on this shield is a way of putting in different supply voltages. So in this video, I'll show you when I measured with 5 volts and with 3.3 volts feeding the resistor, and I could put various resistors in the circuit. And then there's an LED which shines light on the light dependent resistor. So I can measure the forward voltage of the resistor, and then also when I break the circuit, I can also measure the current, right? And so I wanted to see, is there differences in brightnesses? You know, how do these light dependent resistors work? What are the differences between my different resistors? I'd like to point out that I'm not an expert in electronics, so I'm more of a hobbyist. That's why little experiments like this actually help me to learn more about the components and electronics. I also want to point out that these LEDs, I think, are typical LEDs that you can find. I bought them at this website here. It's a Canadian distributor. I do see that they have the same ones that I bought here, the 3mm ones. But also that there are, I just want to acknowledge, there are different materials that go into different LEDs. So some will be very different than what I have here. So for example, the green LEDs that I got here were very dim, but I know that you can get different materials and have much brighter LEDs than the ones I have here. Anyways, let's carry on. So these are pictures of this actual shield when I was using the 5 volt supply. So I took pictures of all the voltage measurements that I was making. I don't think now looking at it that it's really helpful, but I did want to show you some of what I did see when I was doing this. So the top row there, the resistors in the circuit are 100, 150, and 220, right? So lower resistors, brighter lights. When you look at sort of the bright light from the LED, you can't even see the LED itself. They all look kind of similar, and I think what's going on is the camera adjusts how much light it takes in and records, so you don't get a really good appreciation of how bright one is compared to the other. Especially if you look at sort of the bottom row, it's 1000 ohm, 1K, 1000, 10,000, and 22,000. And if you look at the color of the shield, it's all the same shield and it's all taken at the same time. But that green there is much lighter than the top row. So I can see that, the camera's adjusting light. I tried to turn that setting off, but I guess it didn't work. But anyways, you do see that in that bottom row, as the resistance goes up, 1000 to 10,000 to 22,000, that the LED does get dimmer. Like I said, I also measured with a 3.3 volt supply voltage. So here are those same, this is the same LED, the same resistors, the exact same resistors. And you can see those, what it looked like there when I was measuring the voltage. Okay, so here is the data, right? This is the data for a white LED. So this is all the same LED. And I measured at 5 volts and with a 3.3 volt supply. Here are the different resistors. Here, when I was going through just trialing this, I noticed that really there wasn't much current, even with a 100 ohm resistor. So I did add in a 50 ohm. So just two 100 ohm resistors in parallel to get 50 ohms, just to see what that would do. But I didn't go lower than that. So I set it up and I measured the voltage. And I also, at that point, recorded this LDR is what the analog pin is seeing. So the more bright it is, the higher that value is, right? So the highest one is 917. And you can see as the resistor value goes up, the brightness goes down. Okay. And then I took the circuit apart and stuck in my multimeter to measure the current. And so here, these are the measurements for current. And then this LDR2 is the analog pin, sort of the brightness, as measured by that LDR voltage divider when I was measuring the current. So that's how this table is set up. Okay, so this is the white LED. This is the blue LED, so I won't go over this, but if you are interested in data, please pause and have a look there. This is what I got for the yellow, okay, getting dimmer. Here's green. Notice how low these values are. It's starting off at 148. That's the brightest there, even though I'm using the same voltage and same resistors. And then here's red. Okay. So a couple things just to kind of help compare. So typically when you look at, if you go on YouTube and you look at electronic products, people often use a 220 ohm resistor. So depending on what color you have here, right, these are the current, how many milliamps of current that you're using with that 220 milliohm and that resistor for 5 volts. And then here's 3.3 volts. Sometimes I use 1 kilo ohm. So here's 1 kilo ohm. So you can see a lot less for current. And then you don't see this very often, but if you use 10 kilo ohm, the current is much, much less. Okay, less than 1 milliohm. Sorry, 1 milliamp. Another thing that I was curious was if you look at data sheets for LEDs, typically they rate them for 20 milliamps, right? And so if you want a bright LED, but you don't want to, burn it out right away, then you might try to aim for 20 milliamps. And so here are the values if you're using 5 volts. So around 100, 130, something like that. If you're using 3.3 volts, you need much lower. The lowest I measured was 50. So I really couldn't estimate what that was. So if you look at these two charts here, so the one on the left is a blue LED, and the blue line is for 5 volts. The red line is for 3.3 volts. So you can see here, here's 20 milliamps. So at 100 ohms, I got 20 milliamps. Okay, but for the 3.3 volts, I mean, it doesn't even come up to 20 milliamps, right? And so I didn't want to just kind of guess where that line went. So that's why on this chart it says for blue under 50 ohms to get 20 milliamps, right? So I mean, I'm guessing like you could put 3 100 ohm resistors in parallel and you would probably be fine. You'd have to check that, but I think you would be fine. But I don't want to put it in my chart because I didn't actually measure it. Okay. Some of these other numbers are like, not standard, like 55, 60. So again, here's here's 20 milliamps. So for 3.3 and this yellow LED, okay, it's probably about 55 or so. So I tried to pick that off from the graph because it did measure below and above that, the 20 milliamps. Okay, so that's where those numbers come from. So more importantly, what did I learn? So some things I learned about the light dependent resistors. So first thing I want to point out is if you watch that first video, there's a moment where I'm kind of confused because when I was playing around with the light dependent resistor and just checking out how it worked, when I was deciding to make this shield, I noticed that it had a lot of variability. And then when I was actually doing the video, I seemed surprised that it isn't really varying too much, right? Wasn't that much noise. And so a couple things. So first of all, I actually made this device with a switch to be able to switch between individual measurements and averaging over 100 milliseconds, which is hundreds and hundreds of measurements, like more than 800 measurements in 100 milliseconds. And so the point of that was to reduce the noise. Well, I had actually turned that on in the video. I forgot I turned it on. The other thing that I wanted to point out that I thought about later was this. I showed this graph, and it's the bottom across the x-axis is brightness, right? Illumination measured in lux, right? That's the unit. And then on the y-axis is the resistance of the light-dependent resistors. And it's not a straight line, it's a curve. So depending where you are on that curve, you're going to get more or less noise. So if you're in the darker zone here, if you follow this up, right, you're going to get, if you have a change in your light, then you're going to see a change in your resistance of your light-dependent resistor. And that's going to affect the analog reading of the voltage divider. But if you have a similar change out here when it's bright, then you can see that the change, sorry, I can't draw straight lines, is much smaller, right? It's only, this much versus this much, right? So if you're measuring in a brighter environment, you're going to get less variation. Okay, so that's another thing too that I wasn't thinking about at the time when I was doing the part 1 video. Anyway, so that's interesting, right? It's not linear. And then also depending on how bright it is, you're going to see more or less noise. So then to paraphrase that, so you will have more sensitivity with your LDR as a sensor if you're in dimmer light, right? So if you're using a higher value resistor and having less current going through your LED, you're going to, have less illumination, right? So you'll have more signal variability, okay? So if you are trying to make a device, let's say, and for example, you want to measure, the change in light. Let's say you want to detect people through their shadow, right? So as they pass by the light-dependent resistor, there's going to be less light on it, and so that is going to be your signal that someone came and passed close by. But if it's a very bright room, then it's not going to be a big change, right? So some things, there are different light-dependent resistors, right? Different models. So I think, you might have more or less luck depending on which model you have. Also, you could block some of the light. So either having like a translucent sort of screen over top of the light-dependent resistor, so there's less overall light hitting it. And then when the person passes by, there's even less. And I think you'll see more of a change in your reading. The other thing I thought was, if you know that here's your light-dependent resistor and the person's going to always pass on one side, then maybe you could have a shield that blocks the light from all the other directions. So getting rid of more ambient light. And then you just have your light-dependent resistor pointing in the direction where the people will be. And again, less background light hitting the light-dependent resistor, and then probably more sensitive to those to people going by. Anyways, that's just what I thought, where that might have an effect if you're building some device. So I noticed that white and blue LEDs are similar, and I have kind of heard this before, but for example, for the 5-volt supply, if you go from the 100 ohms all the way up to the 220 kilo ohms, the white LED, the forward voltage went from 3.1 to about 2.5, and the blue went from about 3.0 is what I measured to, again, 2.5, right? So very similar in sort of their forward voltages. If you're using 3.3 volts, it went from 2.8 to 2.5, and then 2.7 to 2.4, okay? The yellow, the green, and the red also seem similar in their forward voltage profiles. So those are the numbers there. So 2.2 to 1.8, or somewhere in that range. Okay. And again, in that last point there, the green were really dim, I found, even though you might have similar current running through it. It was noticeably much dimmer than all the other colors. So one thing that I always thought, when I listen to people talk about LEDs and they talk about the range for the forward voltage. So just actually basically what I just said on this last slide. I always thought it was tolerance of it, right? And that each LED had a certain forward voltage, but if you've got a whole batch, you would have a certain range, right? And so the forward voltage will be in that range. But I didn't realize that the forward voltage of each LED would change depending on, the current and the voltage, right? Just like with resistors, if you get a resistor, there's a tolerance, right? Plus, or it's like 100 ohms plus or minus 5%, right? And each one in the package is going to be close to 100 ohms, but it's not going to be exactly, 100. It's going to be plus or minus 5%. So that's what I thought was going on for LEDs, but obviously I was mistaken. Okay, so for example, the for white at 5 volts, it ranged from the 3.1 volts when I had a 100 ohm resistor all the way down to 2.5. Okay. And then the other thing I found is, the higher that resistance and the less current, then it did kind of level off. And even 10,000, 22,000, they had very similar forward voltages. Another thing is, and sort of related, is if you change the supply voltage, but you kept that resistor the same, that is going to affect the current, but then again affects the forward voltage. So you can kind of think of it that way. If I change the supply voltage, the forward voltage is going to change. So maybe I need to change my resistor. But one thing I did find is if you match the current, right? So if I have 5 volts, I have 3.3 volts, and I use different resistors, then if that current was the same, then the forward voltage was the same. It also means that the brightness was the same, right? So even though one's at 3.3 volts and one's at 5 volts, if I used a lower resistor for 3.3 volts so that the current going through the LED was the same, then the amount of light, the brightness was the same. So that's one thing that this LDR was able to show me. So here is an excellent example. So on the screen is a graph with the current, and it's a single LED, right? And it's how much current going through it. And then on the y-axis is the measured sort of what the LDR from the LDR voltage divider, right? The analog voltage. And again, it goes from 0 to 123, but in this case, it didn't even go above 700. But you can see those two lines are basically on top of each other, which kind of surprised me. They do separate there between like 5 and 10, but you can see the blue line, the 5 volt, there are no measurements in that range. So Excel made this graph and it's just measuring point to point, but maybe if there were more data points in there, that they would have been, very close all the way through. If you look, for example, these two data points here that in the yellow circle right now are very close. So there's a picture there. The top one's the 5 volt supply. When there was a 220 ohm resistor, there was 13.54 milliamps going through it, and the LDR measured 482. Well, at the 3.3 supply with a 100 ohm resistor, again, 13.27, so very similar to the 13.54 milliamps. And the LDR measured 484. And so that's why those two data points on the graph are very similar. So that was something that I didn't know. So that was actually kind of interesting to find out. So no matter what the voltage is, if you can match the current for different supply voltages, you're going to get the same brightness. You're going to get, the same forward voltage. So during the part 1 video, I plugged in the multimeter to measure the current, the amperage, and I got the same measurement. But one of the things that I did was I actually measured 10 different white LEDs. I don't think I showed the graph here. 10 different white LEDs, and measured one after another. And so each time I measured the voltage, the forward voltage, recorded what the analog voltage showed for brightness. I took it apart, measured the current, and again recorded the brightness. And so I did that for one after another for 10 LEDs, and then I went back to the first one and I did the same thing again. So each one got a second measurement after I measured all of them. And so I averaged what the sort of brightness was when I was measuring voltage, and the brightness what I was getting when I was measuring current. And it was about 10 units, right? The LDR goes from, the analog voltage, the analog read goes from 0 to 123. So it was about 10, 10 units lower when I measured current. So maybe there is a slight difference when you measure current. Not big, but a slight difference. I did see a lot of variability, even, amongst the different measurements just for forward voltage, and a lot of variability when I measured just current. But when you average it out, the current does seem to be a little lower. Okay, I didn't do any statistical analysis, but it did come out lower. So another thing I found was I've never used 220,000 ohms in series with an LED, and I was surprised that actually many of them you could still tell it was lit, even with that high resistance. So here I showed the different resistor values for the different LEDs. In some cases, though, the measurement for brightness was pretty close to the background light. So things like the red, you might, for a 3.3 volts, you might need something a little lower, like 10 kilo ohms, or maybe something between 10 and 22. I didn't measure in between there. Same with yellow for 5 volts. Some of these here, maybe you need even less than 10 kilo ohms. But where this might be useful is if you are using a battery operated device and you're measuring indoors, and all you need is just to see is the light on or off, you're not trying to illuminate anything, then yeah, maybe you can use 3.3 volts and a 20 kilo ohm resistor, and then your current is going to be way less than 1 milliohm. And so because it's a battery operated device, you want to keep the current draw of your device low so the battery will last much longer, right? So if you just need an indicator, you can use a really high resistor, in some cases like 20,000 ohms. All right, so that's about it. So in summary, things I learned from using this device is that light-dependent resistors, they don't react to light in a linear fashion. And so if you're in dimmer light, you're going to see more sensitivity to changes in light. And for the LEDs, forward voltage is not a fixed value, and it will change with differences in current going through it. And that with the different supply voltages, you can get the same current, the same forward voltage, if you select the right resistor. And lastly, if I did have a low power device and I did want an LED on it, you could use a higher value, even 22,000 kilo ohms to reduce the current draw. And you can still see, the indicator LED. So anyways, that's it for the video. I hope you found it useful. Hope you found it interesting. And I will see you in the next video.